Well, thank you very much. I'm very pleased to be able to give the Bowen lecture. I thought, what should I do for the Bowen lecture? And I thought to myself, well, I don't want to just reiterate what's happened in the past. I want to do something new. And in the last 2 years, I've become very much aware, very much attuned to the fact that Richard and I and a bunch of us old farts will eventually die. And we really need to do something to make sure that this sort of modeling and this sort of model environment and model production can go on. So that's what I thought I would talk about today, sort of an evangelist for computational thermodynamics and mineral thermodynamics. So what I'm going to talk about today is going to be about computational thermodynamics and mineral databases and how they're used in volcanology, geochemistry, and petrology. Now I can see you all glazed over there. And I want you to pay attention to this, because it's actually very, very important. Don't look at the email, don't look at the Facebook. Actually think about the fact that chemical thermodynamics really is a fascinating subject. I've been doing it all my life, and I realize you may not think it's fascinating, but it's really, really fascinating. And even better than that, computational thermodynamics is even more fascinating. Now, you're probably saying to myself that, like Richard, we're both nuts. How can it possibly be interesting? Well, it's interesting because we all do it all the time. Oh, sorry. We have to watch the pretty symbols again. Well, that's kind of fun, isn't it? And the reason it's fascinating is because everybody in this room, I guarantee it, actually does chemical thermodynamics and actually does computational thermodynamics. You all probably use geothermometers and geobarometers, right? Here's an example of the iron titanium oxide geothermometer, where compositions of ilmenite are plotted against compositions of magnetite, from which you can derive a temperature and an oxygen fugacity. You've all used that, right? Give me a sense. You've all used that? Yeah, sure you have. You've all used geobarometers. You've all used zirconium in quartz geobarometers. You've used all this sort of stuff. Well, if you've done that, you have used thermochemical databases and you've used computational thermodynamics. If you've calculated pressures from the water CO2 ratios in melt inclusions or glass inclusions in quartzes and silicic volcanic rocks, you not only have used thermodynamics, but you're really a thermodynamics junkie, because the very basic diagram that you've used, the way in which the experimental data are interpreted, is fundamentally through a filter of underlying thermodynamic theory. Anyone that's used activity-activity diagrams for aqueous solutions or done mass transfer calculations has used computational thermodynamics. And in fact, anybody that's used or referred to or even tried to compute a pseudosection diagram is really deeply rooted in chemical thermodynamics. Pseudosection diagrams have become very, very popular nowadays, particularly in metamorphic petrology. And for those of you that don't know what a pseudosection is, I'm going to show a couple later on. A pseudosection is just a phase diagram plotted in terms of two independent variables for some fixed bulk composition. Here, this is a metamorphic pseudosection, which is in terms of pressure and temperature. But as I'll show later on, pseudosections don't have to be just in terms of pressure and temperature. So my point is that chemical thermodynamics can be used in a wide variety of subdisciplines of volcanology, geochemistry, and petrology. Here, for example, is a pseudosection, a pressure, again, temperature pseudosection. This is pressure in megapascals. This is going to be temperature in degrees centigrade. And here I've computed, or will show you, the computation of this pseudosection using the thermodynamic database of Sticksrud and Lithgow-Bertoloni for the deep mantle. So we don't have to just make pseudosections for metamorphic rocks. We don't have to just make pseudosections for crustal rocks. We can do so for the whole Earth if we have the right thermodynamic database. And on top of this, we can layer computation of seismic properties. We, of course, can layer computation of density. We can layer computation of a wide variety of physical properties and use this then as a basis for understanding other kinds of calculations, like geodynamics calculations. So pseudosections, of course, can be applied to virtually any area of the geosciences, and I wouldn't be standing here today, right, if we couldn't do computational thermodynamics and pseudosections on silicate liquids. So here's an example of a pseudosection computed for a high silica rhyolite. This happens to be the bulk composition of the Bishop Tuff in Southern California, but that's neither here nor there. This again is pressure and temperature, and what we've computed here are little pie diagrams that describe the amount of each phase in the assemblage as a function of temperature and pressure. So over on the right-hand side of the diagram, it's all liquid. Over here on the left-hand side of the diagram, it's various solid phases. And you can see for this particular bulk composition, there is a very drastic and immediate change between all liquid field and the all solid field. And that, of course, if you remember your introductory petrology, is the ternary minimum, the quartz 2-feldspar water ternary minimum in this system. So these are a whole bunch of examples of why you should love chemical thermodynamics and why you probably should use it all the time, because you can do all these really cool things. But what I want to do is stop right now and tell you that despite the fact that we can make all these phase diagrams, despite the fact that we can compute all this solid liquid phase equilibria and so on and so forth, that really is not the main reason we do chemical thermodynamic modeling. Now that may seem as a surprise to you. You're probably sitting there saying, what? Phase equilibria isn't everything. And it's not. The reason we do chemical thermodynamic modeling, the reason we go through all this trouble, Richard just showed you 3 examples that were, in my opinion, incredibly difficult to understand. I'm sure you thought so too. And the reason we go through all that difficulty is because we want to get something else out of the underlying data that we use to calibrate these thermodynamic models. And I want to give you just a brief, actually 2 brief examples of this. The first one is on this slide. What I've plotted on the left-hand side of this slide is the evolution in the redox state, or oxygen chemical potential, in a morb magma, which is crystallizing. It starts off at high temperature, it goes to low temperature. As it crystallizes, I'm calculating the solid liquid assemblage and the equilibrium state of the system as a function of temperature and degree of crystallization. I'm doing this calculation as a closed system. That is, I'm pretending there's no mass transfer in and out of the system. And when you do that, you get an evolution in oxidative fugacity that comes up and then comes down. That is, the system starts off reduced, it becomes oxidized, and then it becomes reduced again. Now, think about trying to do that model experimentally. And all of a sudden you realize that that's going to be a really hard thing to do. Because if you were trying to do a set of experiments where you actually describe the crystallization of the system as a closed system, you would have to keep the total oxygen content constant. That's not what we do. When we do experiments, we keep the oxygen fugacity along a buffer, or we set the oxygen fugacity, or we set the oxygen content. And we don't necessarily do closed system. In fact, experimentally, it would be almost impossible to do a crystallization sequence in a closed system scenario. And yet, that's what we think about. That's what the Earth does. That's how we think magmas behave, right? So if we want to really understand something basic and fundamental, like how does a magma system crystallize as a function of temperature and pressure, yes, we need experiments to calibrate the phase equilibrium, but the experiments cannot be interpreted directly to answer that question. The experiments have to be interpreted through a filter, and that's a thermodynamic filter. And that's why we do what we do. Otherwise, let's just use splines. I mean, why go through all this trouble, right? No, we go through all this trouble because there's a reason behind it. Here's another example. It seems to want to go backwards here, huh? You're going to see all my little demonstrations twice. Here's another example that I think is even more compelling about this. And again, all I'm showing here is a phase diagram computed with this program phase plot, which is essentially does MELTS calculations at each grid point. This is a pressure temperature phase diagram, and again, this is for the high silica rhyolite of the Bishop Tuff. Because we do a thermodynamic model when we compute these sorts of phase diagrams, we can compute self-consistently any other thermodynamic property that can be derived from the basic calculation. So when we do a phase diagram like this, we minimize what's called the Gibbs energy of the system, which is a function of the two independent variables, temperature and pressure. Fine. But what about the derivative of the Gibbs energy with respect to temperature? That's something called the entropy. And we can compute the entropy of this system, and here I've done that and overlaid it as a contour diagram on top of this basic pressure temperature diagram. Now, why is this interesting? Why would you ever be interested in computing the entropy? Well, because the entropy in this system, and all thermodynamic systems, is related to the total heat content of the system. If you compute a thermodynamic model in the equilibrium state, then a change in entropy is exactly proportional to a change in the heat content of the system. So when you look at the entropy varying across the system, you're looking at the heat content of the system. You're looking at a system which has lots of heat, and the heat is decreasing, of course, as the thing cools. But most importantly, the loss of heat, or the change in heat content, is not uniform here. It seems to all pile up right around, hey, guess what, the ternary minimum. Because, of course, that's where all the latent heat is being generated as this system cools. So that's kind of interesting. With the thermodynamic model, we can now not just compute phase relations as a function of temperature and pressure, we can also go in now and look at the consequences, the physical consequences of that crystallization, namely how much heat does the system give off. Or, conversely, we could look at the volume field contoured on top of temperature and pressure. And when we do that, of course, we see other features. We don't see heat content in this case. We actually see the volume change on crystallization, or more importantly, in this particular case, the volume change associated with volatile exsolution in this system. So here we start off with all liquid, which contains a certain volatile content. As the system cools off, it begins to crystallize. As it begins to crystallize, it begins to exsolve both solid phases and volatile phases. The volatile phases have a very large volume compared to the silicate melt or the solids, and as a consequence, the volume change in the system goes up drastically and right at the ternary minimum. So really, you know, that's kind of interesting. So it means that we're going to have to go through this sequence again. I'm sorry. Well, it's kind of pretty to watch anyway, isn't it? Okay. So what's important here is that because we can do calculations like entropy and like volume and so on and so forth, we can now examine the consequences of being able to monitor those two variables and ask ourselves, are they important in a broader sort of a geologic context of the way magmatic systems behave? And here's an example. This summarizes the previous slide that I just saw with the contour diagram. I just happened to pick a pressure of 200 MPa, and you can see how the volume and entropy changes across this system take place as a function of temperature. But importantly, if we think about magma chambers sitting in the shallow crust, for example, if we think of the Bishop Tuff sitting in the shallow crust at a depth of maybe 200 MPa, if we think physically, how does the Bishop Tuff cool? Is it like an experiment? Do we just set the temperature and pressure and calculate the phase equilibria? Well, no. I mean, nature doesn't do that, right? Nature has this magma chamber sitting in the crust, and heat is being conducted out of it, right? And the crust is sort of enclosing this magma chamber and controlling the volume of that body. And it's deformation of the crust that controls the volume of the magma body. It is the rate at which heat can be conducted away from the system, or convected away from the system, that determines the heat content of the magma body. The natural variables, the natural physical variables for describing a magma chamber sitting in the crust are not temperature and pressure. They're not the variables we use for experimentation. The natural variables are heat content and volume, the entropy and the volume. And so what we really want to do is we want to be able to do phase equilibrium calculations in volume entropy space. Now you know that I'm really nuts. Who thinks in volume entropy space? Well, we don't, but I contend that nature does. And it's really volume and entropy that are the independent variables for crustal magma systems. And on top of that, and since there are only two independent variables in any thermodynamic model, if volume and entropy are the independent variables, we're minimizing some energy that then allows us to derive derivatives of volume and entropy. Well, of course, those derivatives are temperature and pressure. So on top of a diagram like this, we can contour now variation in temperature. And you can see that once again, as we pass across the ternary minimum, the place where the liquids goes to the solid phase, we have a distortion in the temperature field that is associated with this crystallization phenomena. And similarly, if we look at the pressure field now, which is a derived variable, and plot that on top of the phase relations, we see a distinct distortion in the pressure field. On this diagram, you should note that since the volumes are high here and low here, this is the low pressure and this is the high pressure. So it's the reverse of the previous diagram. So that really is quite interesting. That means that we can take a thermodynamic model and we can process that model. We can say we can use results from a model where we specify volume and entropy, and we can take the volume and entropy results and put that into a fluid dynamic simulation, for example, or some simulation where we're actually calculating the evolution of that magma body as a function of heat content and volume of the system. And if you think about that, that means that we're actually able to calculate the pressure temperature field and its variation within the magma body. We no longer have to specify that. We can make those derived quantities. And the little calculation I have summarized over on the left, which is from some ongoing work here that I'm doing with Gil and with Joe Dufek, has to do with doing exactly this. This is a fluid dynamic simulation where we have a magma body which is sitting in the crust. We monitor the heat content of that body and calculate phase relations as a function of heat content, and we allow the distortion of the shell that encloses that magma body to reflect some physical phenomena, viscoelastic behavior of the crust. And so the temperature pressure field is derived inside the body, and you can see in this particular case the pressure is going through spikes as the crystallization takes place. And the pressure is always slightly overpressured from the surrounding medium. Well, it's overpressured because it's releasing volatiles, but the spikes have to do with the fact that there's this interplay between the rate of crystallization, which is largely given by the rate of heat flow out of the body, and the rate at which the crust can deforms, which is not necessarily the same rate. So as heat is withdrawn and crystals and volatiles are exsolved, that disturbs the volume field, the pressure temperature field. The pressure may want to go up because volatiles are produced, but the volume of the system that is overpressured may not be able to relax fast enough to keep up with the rate of crystallization. And that sort of thing will give rise to overpressure. And then eventually the system will catch up, or the phase equilibrium will do something different, and the system will under pressure again, and so on and so forth. It will go through these cycles. That really is fascinating, or I think it's fascinating. Do you think it's fascinating? And the reason it's fascinating to me is because, first of all, it's interesting, but secondly, from a computational sort of standpoint, it justifies this notion of actually doing computational thermodynamics. We do this because you couldn't do this experimentally. We go through this horrible, horrible exercise of deriving these solution models and going through all this stuff simply because we want to be able to do things that we couldn't otherwise observe or couldn't do physically in the laboratory. So, isn't that kind of cool? Now I could go on and I could show you example after example after example of this sort of thermodynamic modeling, right? I could talk about the work that we did with Paul Asimov and Ed Stolper back many years ago, where we did adiabatic melting of the mantle, and I could show examples of how constraining crystallization or melting along an adiabat gives rise to all sorts of interesting physical phenomena. We could do other examples involving crystallization of other kinds of basic materials and so on and so forth. But what I want to do here is not do that, because that's sort of self-glorification. What I want to do here is address a problem that really, really concerns me. And that has to do with why isn't computational thermodynamics, why aren't these sorts of calculations done by more people? And what are the impediments to making this sort of calculation more generally accessible to the community? So what I'd like to talk about now is what happens when we want to change a thermodynamic model. People are always coming up to me all the time. They're coming up and they're saying, well, you know, I wish melts could do this. Or I wish we had a solution model to do this, right? I wish we could do thermodynamics of the amphiboles. I wish we could crystallize biotites. I wish we could do this and this and this. And they look at me like a dog that hasn't been fed, and they want to know why I can't fix it. And I want to talk about the reason that we can't fix it easily, and the reason that it's so hard. And I want to talk about a way in which we can make it so that every single person in this room, if they wanted to, could make their own version of melts. And that does exactly what they want to do. Okay? So that's where I'm going here. So, and to give you some examples of this, so suppose we have a thermodynamic model like melts. And suppose we have some calculation that we want to do and it doesn't do it, right? Or suppose we have new experiments. This happens all the time, right? The experimentalists are always producing new data. We would like to stick it into the calibration, and we would like to update the calibration. Oh, I don't know what's wrong here. I could use the keyboard instead. How about that? Maybe that will avoid repetition. There we go. So, well, maybe it won't avoid repetition. All right, there we go. So suppose we have new experiments, or suppose we want to use the tools in teaching, and you've all run across this, where there's some computational tool. I could mention a few names, Thermocalc, that's a little bit difficult to use in teaching, right? I mean, it's just a little bit hard to use. It doesn't mean there's anything wrong with the tool, but there's just this impediment to actually getting it successfully integrated into a curriculum. Or suppose you have your own software model. Suppose, like Richard, you've invented some new model he just talked about for the aluminum, the excess aluminum in magnesium aluminate spinels. And he wants to sit down tomorrow and stick that into melts. Well, right now that's pretty hard to do, but should it be? So I want to talk about how easy it is to update computational thermodynamic tools, and in particular, and I think this is really important, this is something I've been worrying about a lot in recent years, is are we restricted in what we do and what we think about by the computational methods that we have, right? If the computational method only does a certain kind of calculation, for example, Jibba is sitting there, Jibba Ganguly is sitting there, and Jibba says, I want to do melting of the mantle not isentropically, which I think is wrong, but isenthalpically, which I think is right. He has no tool available to him at the moment to do that. And that's silly, because we should explore that issue. And the fact that it would take 6 months to make such a tool is not right, right? We need to have a better way to do that. So, what are the tools of computational thermodynamics based on? I thought I would talk about this simply because I think most people in this room, and I could be understating it, and please, if I'm insulting you, come up afterwards and yell at me. But I think most people in this room would think that what you have in computational thermodynamics is some sort of thermodynamic data. You have a research application or an instruction application, and you somehow get from the thermodynamic data directly up to the research and instruction application. That is, all you need is data. All you need are data. and just a little bit of software sitting on top, and you can somehow solve the problem. That if you just update that data a little bit, you're fine. And the problem is, oh, and then of course, we all hope that there's some communication between research and instruction. But the problem is that this vision does not come close to reality. This is not really how computational thermodynamic models, or for that matter, thermodynamic databases are constructed. The reality is that the thermodynamic data really consists of a number of units. Probably the most important part as far as we're concerned here are the phase equilibrium experiments that actually tell you what phases coexist with what, that we use as a basis for calibration of something like melts, or something like thermocalc, or something like EQ3 or EQ6 for that matter, if you're interested in aqueous solutions. But phase equilibrium experiments are not the only kind of data we need here. We also need information on the fundamental thermodynamic properties of the materials, calorimetric data, which gives us entropies and heat capacities and enthalpies. And of course, if we're interested in high pressure, we need fundamental data on equations of state, volumetric properties, right? Volume as a function of temperature and pressure. If I cast it in this fashion, I think you can see immediately that this sort of thing does not lead directly to melts. It does not lead directly to a comprehensive thermodynamic model for calculating a phase diagram in 15 dimensions. It simply can't happen. There has to be between the fundamental data and the ultimate tool that we use some sort of modeling structure, and this is an intermediate modeling structure. This is a filter where we take the fundamental experimental observations and we process them through models to create expressions for the heat capacity, or expressions for the equation of state, or expressions for the solution theory. There's this intermediate modeling layer. What we call a thermodynamic database sits above this. A thermodynamic database has nothing to do with data. It's a derived quantity. It is a parameterization. We take the fundamental observations that we collect, we filter them through a model, and we quite literally parameterize that model. That is, we extract coefficients by some sort of statistical analysis, whether it be least squares, whether it be Bayesian methods, whether it be guessing. Some sort of method is used in order to filter the fundamental observations. And we call that a database. It has nothing to do with data, nothing to do with fundamental data itself. So when somebody says that we're going to modify a thermodynamic database, they're not actually sticking in new numbers there. What they're doing is they're working down at this level, and they're going through a great deal of trouble in here in order to produce a set of final outcomes up there. Now, the real dangerous thing is that the stuff that we use, melts, EQ3, EQ6, thermocalc, all that stuff sits on top of the derived thermodynamic database. So there really is quite a number of layers of material or of activity between the stuff that we use and the primary observation. This really is the problem, right? And the central problem here, as a problem as far as I'm concerned, you may think it's fine. You may say, oh, just give me melts, that's fine. I can use it, that's fine. But the problem to me is that the arrows are all going upwards here. Now, why is that a problem? Well, that's a problem because everybody is using all of these tools. Everybody. There's a large number of people that are using all these tools that sit here at the very top. There's a crowd of people using all these tools at the very top. But because the arrows are all going upwards, and because there's this unbelievably complex series of steps to go from primary observation through the thermodynamic modeling to the construction of the software and so on and so forth to get up to here, that hard stuff is being done by a small number of people. I call it the few, and these are the many. And the problem here is that the situation is not sustainable because the few are trying to do all this stuff, they're trying to produce all this stuff, and the more the many use this software, the more challenges, the more modifications, and the more interest there is in participating in the development of the underlying software infrastructure. We've been going on like this with data going through a few people, and literally it's a few people. You can sort of count them on two hands, right? The data going through a few number of people to be used by a large number of people. We've been doing this now for 10 years. It's getting more and more, 20 years. It's getting more and more complicated, more and more difficult to modify, and what's going to happen? Well, let's think about this for a second. So if new primary data are available, or the user community wants something to happen here, well, what happens is that it doesn't happen, right? The few who are actually doing this stuff are just not going to respond as fast. If the user community wants to participate in the production of these models, well, the problem is that the actual production of the software or the modeling infrastructure itself is not necessarily documented well. And in particular, the actual process of creating these models has some intuition built into it. It's just inevitable, right? We all make decisions when we do research. But the problem here in building these tools is that if I make a decision, which may be arbitrary, in building these tools, all the people that use it are stuck with it. And that is not a particularly good situation to be in. So I can't read that from here anymore. But you guys can read it from here. Oh, there we go. Yeah. So the problem is that the expertise and vision of the community is neglected in doing this. And the difficulty is, the ultimate difficulty is that the few are going to die, and then models become ephemeral. Thermodynamic databases are created. People forget how they did it. People throw away the punched cards that it's based on. They throw away the paper tape. They put it on floppy disks that are no longer readable. It's just not a situation that's going to help us. So what I want to address in the remainder of the talk is how can we take this oligarchy of the few model creators, and will they forever dictate the research and educational needs of the community vis-a-vis computational thermodynamics and thermodynamic databases? And I say no. That's just not right. That currently we have advances in cyber infrastructure that are actually going to allow us to make this development of thermodynamic databases and CT modeling tools democratized, that is, available to everybody. And I hope you all agree. Some people don't, actually. I've talked to some people about this, and they say, no, we don't want to let the community do this. But I hope that you all agree that this is a good idea. Do you sort of agree this is a good idea? That we should have... You don't. There's sort of, it's interesting. There's a mixed thing here. I think it's a fantastic idea, and I'm going to do it, so I don't really care whether you like it or not. But I think it's really, really important that everybody participate, and I'll try to justify why I think that's so important. But let's give this to me for a second. Let's give this to me that this is a good idea, and how can we make it happen? And the way we need to make it happen is we need to change the way in which we do thermodynamic model development. We need a new paradigm for this. And I think the paradigm is we need a software infrastructure that actually provides access to the fundamental experimental data. And by that I mean not just the phase equilibrium data, the calorimetry data, the equation of state data, and so on and so forth. Do you realize that at this moment in time, you could not go to the web and find the basic calorimetry data for minerals or melts or gases? You couldn't do it. It's not there. It's clearly been done and systematized many times in the past because there are numerous thermodynamic databases, but all that information has been lost. None of it has been saved digitally. Well, That's the first thing you need if you're going to make it easy for the development of these sorts of things. What else do you need? You need to be able to say, you need to be able to have a software environment where you can sit down and say, I want to make a new thermodynamic model for amphiboles. You need to be able to type in the free energy of expression for an amphibole and not have to worry about it from that point on. Forget about taking derivatives, forget about coding anything, forget about doing anything, right? It all happens automatically. In the words of Apple, it just works. We need to be able to have a software that maintains thermodynamic consistency when we derive a model, so that we can't just do anything arbitrary when we construct a thermodynamic model. We've got to obey the Gibbs-Duhem relations. We have to have all the cross-partial derivatives correct. We have to do all this stuff that Richard and I have worried about and had to think about consistently over the last 20 or 30 years. And it's just an impediment to bringing new people into the field to do it. We need to get rid of that. We need to have it automated. We need to be able to construct a model that self-documents. This nonsense of sitting there and just trying a bunch of things and forgetting what you've done and then eventually writing it down. And of course, we all know that we never publish a paper exactly the way we actually did the work. That would be sacrilegious. We always publish a paper in a very neat and wonderful fashion that describes exactly how a logical person would go about doing this, but that isn't anything like we actually did it. You need to know how you actually do it in order to understand how to make thermodynamic models. That needs to be recorded, and the only way to do that, a person doing the work can't do that by hand. It's just too tedious. It impedes the thought process. So you have to have that done automatically. We need to be able to generate thermodynamic models and immediately, I'm saying immediately, be able to look at the result of that model in terms of a petrologic outcome, right? A real outcome. And importantly, and I'm going to show you an example of this, this is not just fantasy, importantly, we need to be able to take the extrapolated outcome of the model that we've just created, or the infrastructure we've just created, and be able to see what that looks like and interact with that extrapolated outcome. Why? Well, because another reason for making thermodynamic models, besides investigating stuff that we can't do experimentally, is we can extrapolate experimental results to pressure temperature conditions, let's say, that we can't investigate experimentally. But that extrapolation is important to the construction of the model. The outcome of that extrapolation is. And we need to be able to analyze that or deal with it. So the bottom line is, in my view, for computational thermodynamic models like MELTS or like EQ6 or like Thermocalc to be useful, they need to be reproducible, and they need to be released not just as a model, but they need to be made available as a software infrastructure that allows anyone to update that model in a self-consistent fashion. So, is this just pure fantasy, right? I mean, have we really advanced in cyber infrastructure and computational methods to the point where we can actually do this? Can we really build this sort of software infrastructure that demeans or diminishes the necessity of the oligarchy and actually makes democratization of this process a viable one? And yes, we can do that. Yes, the cyber infrastructure has increased to this point. And the reason that we can do this is because now we can actually build software tools that are as visually interactive and with the same kind of visual feedback as the tools we build to describe forward outcomes of the model. So MELTS immediately gives you a visual feedback as to what the phase relations are. I showed you a few of those, right? Well, why not actually build software tools for calibration that have exactly the same kind of visual feedback? And I want to show you an example. At the risk of boring you, I want to show you an example of how to actually calibrate a fusion curve using software tools that are completely visual. and that give you a sense of how to do thermodynamic modeling without having to worry about all the underlying equations. So what I've got here, just to set it up, this is a pressure temperature diagram. The blue dots here, can you see the blue dots? You can see the blue dots. The blue dots are places where solid forsterite are stable in pressure temperature space. The red dots are places where liquid forsterite is stable in temperature pressure space. The cyan dots are places where you have presumably equilibrium coexisting between liquid and solid. This black curve here should go through the place on that diagram where the blue dots turn to red dots. The act of making the black curve do that is called calibrating the fusion curve. The fusion curve is going to be based on thermodynamic data for solid forsterite and liquid forsterite. All right? So we're going to assume for this little exercise here that we know everything there is to know about the thermodynamics of solid forsterite. Let's just take that for granted and only worry about the liquid. And in fact, for the liquid, we're going to assume that all the properties of the liquid are known, which they are, except for one very critical property, and that is the pressure dependence of the energy, of the Gibbs energy of the system. And that translates to not knowing what's called the equation of state, the volume as a function of temperature and pressure for the system. So what we're going to do right here, right in front of you, I'm going to do it. We're going to calibrate the equation of state for forsterite liquid using these visual tools. First of all, what is the equation of state that we're using? This is the only equation I'm going to show you here today, and I only show it for one reason. This is the Vinet equation of state, which I'm going to use for the liquid. Equation of state, pressure, volume, and temperature, right? All related to each other. The parameters of this expression, that is, the things that we need to calibrate, are the bulk modulus K, the volume of the system at low pressure, the derivative of the bulk modulus with respect to pressure, which is K prime, and the thermal coefficient of expansion, which is alpha. There are 4 parameters in this equation of state, just like Birch-Moynihan, except it's a slightly different functional form. 4 parameters, those are the ones we need to calibrate. So I show you the equation because I want you to see quite clearly that the parameters are nonlinear in this equation. This is a complex expression for the pressure. In order to calculate the energy of the liquid, you have to integrate this expression, first of all, with respect to volume. And after you do that integration, you have to add it in to the temperature-dependent properties for the liquid. So it becomes a very, very complex nonlinear expression. And most of the time when we fit equations of state, we just use Excel or some sort of numerical program, MATLAB, and so on and so forth, and we digitize all the information and we fit the equation of state and so on and so forth, and we get an answer. Right? But the problem here is that you notice that there are these error bars here associated with these data points. So how do you incorporate the error bars when you do that? Well, you got some weighting technique, or you use this or that if you're very sophisticated. You use Bayesian statistical methods. That's all the rage nowadays. But I mean, I can just see it. I know where the curve has to go. The curve has to go between the blue dots and the red dots. And let's hope it goes through the cyan dots. And then that's it. No muss, no fuss. So let's just do it. Let's take the bulk modulus and let's vary it over a range. And let's watch and see what happens to the curve. And you can see that we're doing it. But you realize what's happening here. I'm changing that parameter. And this is actually in real time. I am actually calculating the curve in real time. Now, if that isn't cool, you're asleep. So let's try another parameter. Let's try the derivative of the bulk modulus. Well, of course, as you would expect, right? That's not going to really be applicable at low pressure. It's really not doing very much at all. Well, that's sort of interesting. So finally, let's explore the space, and let's now look at the thermal coefficient of expansion, which has a remarkable effect. And then we can look at the bulk modulus again. Here we're changing the bulk modulus. Now we're changing the bulk modulus. And so we fool around here, and all of a sudden, we're done. We've calibrated the equation of state. The correct parameters are described over here. We've done it in real time. We've done it without having to use any sort of numerical program, and we're sort of visually satisfied with the result. But now, most of the time, we do this sort of analysis. For example, in building the MELTS database, we do this sort of analysis because we're interested in how this how this function extrapolates in temperature, pressure, space. So on the next slide, let's actually do that. Let's change the pressure scale so that we go up to a much higher pressure. And let's go over to the parameters again. And let's see if we can get the function to still obey the data, but perhaps do something more interesting at high pressure. And in fact, what I'm looking for here, as you might suspect, is I'm looking to see if I can actually get the curve to turn over at high pressure. Are there some set of thermodynamic parameters that allow me to do that? And in fact, there are, right? I've just changed the derivative of the bulk modulus, which you would expect to be the most operative variable at high pressure, to a value where we can get a turnover in the density relations of the liquid and solid at high pressure. Now, of course, there's no data up there. So that's where we want to put it. But we may have an application. We may be building a model of the Earth where we would like to see, we would like to test, do these sorts of liquids, right? Do olivine-like liquids actually go through a density inversion at some particular temperature and pressure? So this might be a model building exercise to test the consequences of that very turnover. And we might want to put that very turnover in a specific spot. So, do we really have to play with these parameters one by one and guess which one should be done and so on and so forth? Well, no, we don't. Why don't we just build calibration software that does this? We go and we check off all the parameters that apply to the equation of state. We go up to the curve in question, we highlight a point in that curve, and we just drag it around. At the same time, come always updating the equation of state parameters to be self-consistent with that, and always maintaining internal consistency with the underlying thermodynamic data. Now that's just cool. This is the sort of software that we need to build to do thermodynamic calibration. I have two more examples here. The one up at the top is dealing with PT sections and dragging around the phase boundaries for the aluminosilica system. The one on the bottom here has to do with dragging around solution or dragging around the curve and updating thermodynamic parameters that describe a solvus in a system which also contains a phase transition. And one of the interesting things here is that I'm dragging around this side of the curve, but because of the self-consistency of the underlying thermodynamics, I'm actually doing unusual things to the position of the phase transition curve. So the point is that this sort of software can be used to not only just calibrate the immediate thermodynamic model that you're interested in, the immediate relations you're trying to fit, but also investigate the consequences of changing those parameters to fit one section of the curve on what happens on the other section of the curve that's dependent upon it. The point of showing you these examples, and by the way, if you'd like to see these examples, or if you would like to know how I'm doing these calculations so fast, because these are Gibbs energy minimization calculations that are being done at what I like to call the speed of thought. Come see my poster tomorrow afternoon in the Earth Cube section, and I'll show you how this is done, and I can actually demonstrate some of this on my laptop. These are not being done on a supercomputer, by the way. These are being done on laptop-level machines. So the point is to show you that, that these things can be done very, very rapidly, and that at no time are the underlying thermodynamic consequences of this being compromised. And that I think is really, really important. So when I end in the last few minutes here, last few minutes, is a sense of my vision of how we can create a modeling environment for the production of thermodynamic models like this that is more accessible to the community. We started off with this notion that there are these phase equilibrium experiments, there are these data sources that somehow give rise to research and instruction applications. And what I want to do is not say that there aren't those data sources, but what's important is that those data sources be available online and that they be intercommunicating with each other. It's important to have the basic data accessible in some sort of digital format and accessible in sort of computer terms, accessible directly to interrogation. That is, they have to be in some sort of relational database that we can go in and search and bring up those properties and use them when we need them. But most importantly, we need this. We need some sort of platform. We need, it could be web-based, but 5 years from now, maybe the web won't exist anymore. We need some sort of platform that we can all access that allows for this development of this modeling software. It allows for a direct interrogation to the underlying databases. It allows you to construct models, document them, test them, so on and so forth, and then make them available to the research community and the instruction community. And the way that should be done is not through the distribution of a physical program, or not through going to a particular person and asking them for the software, or not begging for it, or not so on and so forth. The actual act of model generation should generate models automatically, and those models should be in the cloud. They should be accessible to sort of client sort of applications that run in browsers or that run on desktops. And that kind of environment means that every time you update data in here, you can take an existing model and update it here. It will automatically be generated and stuck in the cloud for computation. And then all the resources that, or all the software that's used in research and instruction could immediately access both of those things and decide whether or not it's a valid new model, whether or not it should be updated. There's no reason that we should just accept what somebody else gives us anymore. There should be an environment that allows this sort of thing to be used by everyone. So here's how I think this sort of infrastructure would affect users. Thermodynamic databases would no longer be static. They would be mutable objects. If you don't like a thermodynamic database, there should be tools available to add new information or change it or update it and do so in a self-consistent fashion. The tools that we create that are built on thermodynamic databases, and I pick on MELTS because I can pick on myself, but you could put EQ6, you could put Thermocalc, you could put anything you like in here. Those should not be static. If you don't like the results produced by one of these modeling packages, you shouldn't complain to me, you shouldn't hit your head against the wall, you shouldn't go off and not use them. You should be able to change them to do what you want. And as a consequence of all this small group of people that actually generate these sorts of models will be deprecated, to use the computer science term. And that's good. And I think it's really good. We could argue about this afterwards, but I think it's good because the more expertise you actually bring into the formation of these things and the evaluation of these things, the better the models get. When we create these things, you can't always think of all the things that people might do. You can't always think of all the applications people might have. You may want to do silicic rocks at high pressure, right? And I never thought of doing that, but you did. And you want to make sure the model works there. And you want to be able to change it so that it does work there. And that's important to be able to do. So the bottom line is that, you got these guys, Ghiorso and Sack. You got these guys, Holland and Powell. You have some others. Well, as far as I'm concerned, they're obsolete and they can rest in peace. I want to make it so that we don't need them. I want to make it so that all this oligarchy of developers is just not necessary. So what I tried to do today in this talk, as bizarre as it was, is to hopefully convince you that every single person in this room, whether they like it or not, has actually used thermodynamic databases and computational thermodynamics. And that more likely than not, your research is probably integrally dependent upon them. That computational thermodynamics is not just done to reproduce phase equilibria in pressure temperature space. That's fine. I mean, it's fine to use it for those purposes, but that's not the real reason we do it. We go through this thermodynamics filter, we go through this modeling exercise, which always compromises the underlying veracity of the thermodynamic data, experimental data. It always does. We're always making compromises. We always average things. We always throw stuff that doesn't fit away. We do all this stuff. So you lose something about the fundamental data when you do a thermodynamic model, but what you gain is this ability of an extrapolation and valid extrapolation, and what you gain is this ability in doing calculations or doing simulations that you simply cannot do experimentally. And finally, I hope I gave you a taste of my new evangelical spirit to make thermodynamic, computational thermodynamic tools and the calibration of thermodynamic models more of an exercise for the community and less of an exercise for the few. Thank you very much.
Well, thank you, Mark, for a very inspiring lecture. And we have 3 minutes for questions. So, are there any questions? Yes, Jiva, please.
Yes, I mean, the idea would be to, if you make a change like that, you would be able immediately to look at all possible outcomes, right? All possible consequences of making that change. So that's a sort of a vague statement, but let's say you change the fusion curve of Forsterite. Then you should be instantly able to calculate the melt productivity in the mantle that results as a function of that change, and see if that makes any physical sense. Or you should be able to calculate a phase diagram that depends on olivine and see if making that change has drastically altered reality or your perception of reality under some other pressure temperature conditions.
Question at the back.
So, Mark, that was so inspiring. We're all sort of sitting in this wilderness or this endless vista that you've exposed to us, trying to come to grips with the millions or trillions of model runs that will be necessary to find our path through this. But so I'm just wondering, if, as I manipulate the compressibility of Forsterite liquid or whatever it might have to be, are you calculating the residuals? I mean, let's imagine that this is really an internally consistent database for innate components or whatever. Are you calibrating the residuals through that internally consistent data for every single?
But believe it or not, well, now in the case that I showed you, right, and this is to a certain extent prototype software. In the case that I showed you, there was, as you moved that curve, simultaneously there was a linear regression going on as far as the underlying data points. So yes, we were in a sense satisfying the data points in that diagram, but in general, what I envision is moving that curve and satisfying all possible data points.
Single equilibrium involving force.
Exactly.
And all the downstream.
Yes.
Yeah.
And that's a formidable task, but it is not beyond the capabilities of current compute clusters and so on.
In a way, that was the power of linear programming, that you weren't just using the fusion curve of Forsterite to calibrate the fusion curve of Forsterite.
Right.
And so I'm sure you don't mean to lose that, but
Right.
it's, anyway, that was super inspiring. I just can't say enough. But so in PetDB, the last time I used
No, they're
You've got to benchmark these models.
Oh,
so that when
yeah.
you publish a paper, you don't have a supplement.
no. I think there
Make
always
the weights large.
right. There always has to be something like that. There always has to be a set of models that sort of are approved by experts, but then you can go from there.
Oligarchs, we need you.
Well, thank you. No, I think what Peter brings up is a very important point. You need to start from somewhere. You can't start from scratch. But what you can do is you can modify. And then what I envision is a modeling community infrastructure where groups of people can share models, and where models can be tentatively published and evaluated by a broader community, so that if there are problems that are created by doing something which you shouldn't have done, they're unearthed. And then the model is set aside and for something that works better. But it is very, very true that because all these models are approximate descriptions of the energy of all these surfaces, all of them, without compromising the integrity of the model too much, can be modified in such a way that they work better in certain regions of pressure temperature space or in certain regions of composition space. And that may be what you want for the moment. You may not want melts, which is supposed to be general for all compositions. You may want something that just works for Morbs. Well, then we'll just make it work for Morbs, and you can use it just for Morbs, and that's fine.